So scientific measurements. I just mentioned that, the mass and the volume of that ring, those measurements are not exact. In scientific measurements, pardon me? Yeah, see, closing the door does help, but then, I don't know about you, but I'm really warm. Are you guys warm? Yeah. I'm actually surprised we went almost an hour without a train. Anyway, okay. Scientific measurements. We record them so that every digit is certain and the last digit is estimated. So we acknowledge there's uncertainty in every measurement, and we just embrace that. We go with it because we can't do anything about it. The last digit in any scientific measurement is understood to be an estimate. I really don't want to talk about carbon monoxide. Let's just skip that. So how many digits get recorded depends on the device you're using to measure. So let's look at this little inexpensive kitchen scale, and we're measuring 1 pistachio. So we're going to ignore the ounces side because that's English, and this is chemistry class, and we're going to always choose metric if we have a choice. So over here, this little black line is the one that moves relative to the scale behind it, and we have to figure out, what does this mean? Well, the first big line is 0, and this next large line is 10, and in between, each red line represents 1 gram. Pretty sure everybody's okay with that. So we find the black line, and we see that it's between line 1 and line 2. That tells us that the mass of this pistachio is more than 1 gram, but less than 2 grams, right? So it's 1 point something. Is there any uncertainty in the 1? No, it's between the lines. There's actual lines there. There is no question, you cannot argue. It's between 1 and 2. We have to include an estimated digit, though. So we're going to estimate between there, and the author has estimated that it's 1.2. Now, we could argue a lot about whether it's 1.2 or 1.3. People are going to have different opinions. It's okay. It's an estimate. It's not perfect. So we record it as 1.2 grams, and when I look at that mass, I say, oh, it's definitely at least 1 gram, and they have estimated that it's 0.2 above that. But there's some uncertainty there. Everybody okay with that? This is what we call reading between the lines. So we are reading between those 2 little red lines. We read between the lines. This is going to be important in lab. We're going to be doing a lot of measurements, mostly of liquids, where you have to read between the lines. And some students just have a hard time getting into their minds. You got to estimate between. So the basic idea here is to estimate 1 decimal place past the smallest division. So I'm going to highlight that. That sentence right there is your guideline for how to read any non-digital device. We call those analog devices. So you look at the smallest divisions. Here, the smallest divisions represent 1 gram. So then I'm going to record that 1 decimal place further, which would be the 10th. If I'm looking at a ruler where the smallest divisions are 0.1 centimeters, I'm going to estimate the next place, which is the hundredths place. If I've got a thermometer with 1 degree markings, I'm going to estimate the next decimal place. Does that make sense? So let's practice. So here's a thermometer. I'm going to tell you this is degrees Celsius, not Fahrenheit. So what would this temperature be? Well, we see that it's a little hard to see. It's almost behind the 100 here, but there's the the red liquid. It's actually alcohol. And so here's 100. This is 110. What do each of these little black lines represent? 1 degree Celsius. So the markings are 1 degree. So what do we need to estimate to? 0.1. So we're going to estimate to 0.1 degrees. So we look at the mercury, and there's 100, 101, 102, 103. So it's definitely closest to 103. It looks like, and we could argue about it, it looks like it's either exactly on 103 or maybe a tiny bit higher, right? So it's 103. And then we need to estimate the next place. What do you think it is? 0.1, okay? That's a valid reading. Anybody think it's 103.0? It looks like that to me, but that'd be okay. We need to write this digit even if it's 0. Because if I just write 103, as I say, well, it's right on 103. If I write it like this, and another scientist looks at it, they're going to say the uncertainty is in the ones place. And they're going to say, well, that means the smallest division was every 10 degrees, and they were estimating the 3, and that's not what we mean. So that would not be a good one. So any questions about the thermometer? Yes?
So would 103.6 be wrong?
103.6, I would definitely argue with you about that. Because when we, see if I can draw a line. If you draw a line where the right side of that green line is the end of the red, 103.6 would be a little past halfway between 103 and 104, right? So that would be over here, and it's not there. Would I mark it wrong if you wrote that down? Probably not. I'd say, well, maybe you need to get their eyes examined, but if that's what they think, yeah.
So 102.9 degrees would be acceptable?
102.9 would be more reasonable than 103.6. Yeah. There's uncertainty. We cannot say exactly what that is. So here we have some water in a graduated cylinder. And the unit here is milliliters. So water in a glass container has this curve, and that curve has a name. It's called a meniscus. I'll explain later in the semester why water does that. But it does that, and so the glassware is calibrated to be measured to the bottom of the meniscus, the bottom of the curve, the lowest part. You also have to be careful when measuring liquids that you get your eye down and you're looking straight across at it. So here's your eyeball, and you're looking straight across. You don't want to be looking down or looking up, because that can cause an error in the measurement. So we're looking at the bottom of the meniscus, and here we're evaluating. This is 4 milliliters, and this is 5 milliliters. There are 10 little white lines. What does each line represent? 0.1 milliliters. So the lines are 0.1 milliliter. So what am I going to estimate to? 0.01. So it's definitely more than 4, right? It's between 4 and 5. I'm going to say it's 4 point, and then I can read the lines, 1, 2, 3, 4, 5, and it looks like it's between the 5 and the 6. So it's 4.5 something. There's no uncertainty about that. We can all agree on that. Then we read between the lines. We have to estimate. Anybody want to give an estimate? 3. I think 8 would be better. 4.58 milliliters. Because what we're trying to do when we estimate between is we're trying to imagine that there's 10 little divisions. And so I think that's clearly more than halfway towards the next one. So I would say it's definitely more than 4.55. And then it's just kind of a guess. Any questions? So the precision of a measurement depends on the instrument used to make the measurement. And we just demonstrated that. When we take measurements and we do calculations with them, crazy things can happen, like we saw with our calculations already this morning, that we end up with all these decimal places. And then if we put that result down and just include all the decimal places our calculator spit out at us, that can give a false impression of the precision of that result. The precision should not be affected by calculations that we do with the numbers. So how do we keep track of that? Well, significant figures is a method of keeping track of that does not require differential calculus. Students do find it somewhat confusing, but once you understand it, and I am here to help you understand it, it's actually not bad at all. It's much simpler than other methods. It's not a perfect method, but it's the go-to rule of thumb method that we use for keeping track of precision when doing calculations. So what we mean as significant figures are the non-placeholding digits in a recorded measurement. They're all the certain digits, and they include that one estimated digit. So if you have more significant figures, you have more certainty in your measurement. So we have to learn to determine what constitutes a significant figure, because it's the non-placeholding digits, but that's not always really obvious. So here's some rules. It's really only the zeros that mess us up. So all non-zero digits are significant. So examples in these numbers, they've bolded the non-zero digits in case we couldn't tell that they weren't zero. Then the zeros. So there's 3 kinds of zeros. Did you know that? There's 3 kinds of zeros. They all look the same, but it depends on their place in the number. There are zeros that are on the interior of the number. I also think of them as trapped zeros. They're not at the beginning, they're not at the end. They're trapped between non-zero digits. So here, 3403, that 0 is an interior 0. This number, 3.02205, those zeros are both trapped interior zeros. Those always count. They are never placeholders. There are leading zeros. These come at the beginning of a number. They lead the number. Those are always placeholders. They're just there to hold the place of the decimal point. So those are never counted as significant figures. So any zeros at the beginning, don't count them. Okay? Always count the ones that are trapped in the middle. Never count the ones in the beginning. And then it's the ones at the end that really give us grief. So these are my rules, which are slightly different than what the text explains it. It gives the same result. If my method doesn't work for you and the text method does, that's fine. Use that one. Doesn't matter how you think about it, as long as you come up with the right answer. So this is how I think about it. So if there's a decimal point that's actually written in the number, then all of those trailing zeros are significant. So here we have several examples of numbers where there's an actual decimal point. All the zeros at the end are significant because of the decimal point. the decimal point is written. We don't need those zeros to tell us where the decimal point should be. If you have a number with trailing zeros, like this, 300, 300, no decimal point. What are those zeros doing? They're holding the decimal point, right? They're holding the decimal place. If we got rid of them, it would be 3. 3 and 300 are not the same. Does that absolutely mean that those are not significant figures? No. What it means is they are ambiguous. It's not clear what they are. When we're faced with an unclear situation, we want to assume the worst, so that if there's a problem, we err on the side of caution. And so we're not sure if these are significant, so we're saying they're not. We're saying, well, we'll assume that they're there just to hold the place of the decimal. So this number, 238,100, again, those zeros are to hold decimal places, and so we're not going to count them as significant figures. We would like to avoid writing numbers like this because of the ambiguity. But the fact is, we're going to run into them. So any questions? So significant figures deal with measured quantities. There are also numbers that are not measurements. They are exact numbers. An exact number has no uncertainty. And so significant figures don't really mean anything for an exact number. So what we can do is we think of an exact number as having an infinite number of significant figures. So there's 3 kinds of exact numbers. Exact counting of discrete objects. Okay, so how many Sharpies am I holding up? 2. Are you sure? It's not 2.5? It's not 5? No, it's exact. We can count them. 1, 2. So if I wrote how many Sharpies I have, I could write 2.0000. It's exact. I could write as many zeros as I want. Well, that's a waste of time to write all those zeros. If I write down 2 Sharpie markers, I know what a Sharpie marker is. I know that's an object that can be counted. So it's exact. If I say 2 pounds of butter, is that exact? Can you count pounds of butter? No. You say, well, I can count 1 pound packages of butter. No, that's different. Does that 1 pound package of butter weigh exactly 1 pound? No. It's close. It's not exact. So, counting of discrete objects. Just because something has a whole number, this is 5 meters long. It's a nice whole number. It looks like an exact number. No. Meter is a unit of length. It's measured. It's not exact. Okay, so that's one example. That's going to show up on the worksheet today. Integral numbers that are part of an equation. Integral meaning integers, whole numbers. So an example would be the diameter of a circle is equal to 2 times the radius. This is an equation, and it has an integer in it. That number is exact. Okay? When we look at the temperature conversion between Celsius and Fahrenheit, the 32 and the 1.8 are actually exact. Other examples are defined quantities. So in the metric system, the prefixes are defined. And so when we say that 1 milliliter is equal to 10 to the minus 3 milliliters, I'm sorry, that'd be dumb, liters. It's defined, that's exact. So sometimes you'll see 3 lines in the equal sign is exactly equal to. So some conversion factors are defined quantities, others are not. Within the same system of measurement, within the English system or within the metric system, the conversions are exact. So 1 foot is exactly 12 inches. It's defined that way. But when you look at the, let's go back there. When we go back to this table, here converting kilometers to miles. This is an English unit and a metric unit. This is not an exact conversion. If you look up that relationship in different books on the internet, you may find differing numbers of digits in that relationship. One might say 0.6 miles. Another might say 0.62 miles. They're expressing it differently. It's not exact. The exception when you're going between systems is this one, the inch and the centimeter. Here it says exact. That conversion is used so frequently they actually redefined the size of the inch so that it is exactly 2.54 centimeters. So that one's exact. Otherwise, if you're going between metric and English, they are not exact, and you do have to think about sig figs. Oh gosh. Sorry for all the flashing around there. Okay, so let's practice what we just learned. We need to identify how many sig figs are in each of these numbers. So 554 kilometers. 3? Yeah. How do we know that? Well, there's 3 digits, 5, 5, and 4. None of them are zeros, so they're all significant. That's not an exact number because kilometer is not an object that you can count. It's a measurement. How about this one? 1.01 times 10 to the 5th meters. 3. So this is in scientific notation. This times 10 to the 5th is all of the place-holding stuff. The significant figures are in this coefficient part. The beautiful thing about scientific notation is all the digits before the times sign are significant and the 10 to the something is not. If we were to write this out, it would be 1, 2, be 101,000 meters. These zeros here are ambiguous because there's no written decimal point. When we put it in scientific notation, we don't worry about the ambiguity anymore. Questions? 1.4500 kilometers. There are those zeros. It's 5. So zeros at the end. My rule is if there's a decimal point physically written in the number, count the zeros at the end. This one has a decimal point, so we're going to count them. So there's 5 digits there. 7 pennies. Exact. You can count 7 pennies. There's no uncertainty. So how do we answer this? How many sig figs? Infinite. So we could put the infinity sign. We could say unlimited. On the worksheet we're going to do today, if you say exact, I'm going to be fine with that. How about this one? 0.00099 seconds. 2 sig figs. These zeros at the beginning are never counted as significant figures because they are always there to hold the decimal place. Yes. We could put this in scientific notation, 9.9 times 10 to the minus 4. seconds. Then it's much easier to see that it has 2 sig figs. It's these guys right here. The place-holding zeros all get encompassed in that 10 to the minus 4. 21,000 meters. If pressed, I would want you to say 2. Technically, it's ambiguous. We can't be sure. It would be better to write this in scientific notation. 2.1 times 10 to the 4th meters. Because then we get rid of those ambiguous zeros. So here's just a little tip, I guess. When students are converting between decimal notation and scientific notation, there's often some confusion about when is the exponent negative and when is it positive. And the book talks about moving the decimal right and left, and that doesn't make any sense to me. This is how I remember it. So here's the scientific notation, and here's the original number. Look at the decimal form of the number and ask yourself, is that a big number or a small number? 21,000. It's a big number. Well, relative to what, you say? Well, relative to the number 1. It's big, right? How does Mrs. K feel about big paychecks? Positive or negative? I feel positive about big paychecks. I love those guys. Positive exponent for a big number. Look at this one. Big number, small number? Small. It's smaller than 1. How does Mrs. K feel about small paychecks? Negative. Okay? So if you think about that, you'll never mess your negatives and positives up again. So when we do calculations, we shouldn't be losing or gaining precision. And to keep track of that, we have to have some rules of what to do with our significant figures. So multiplication and division are related mathematical operations. You could think of them as the opposite of each other. They're very similar in their concept. So they have one rule that covers both of them. The result, the answer, has the same number of significant figures as the factor with the fewest significant figures. So for multiplication and division, we're counting sig figs. What we'll see with adding and subtracting is that we're counting decimal places. Multiplication, division, we're counting sig figs. So here are 2 examples. So we've got these numbers, we're multiplying them. Calculator gives you something like this. Go ahead and write down what your calculator says. Then go back and evaluate the sig figs. So we're going to look at this one. This one has 4 significant figures. If you're not sure about why these have the number of sig figs, please ask me and I'd be happy to explain it again. This one has 5. This one only has 2. So then you ask yourself, which is smaller, 4, 5, or 2? 2. 2 is smallest. This one has the fewest number of significant figures. It only has 2. My answer can only have 2 significant figures. Okay. Here's another example here. We're dividing 5 sig figs, 3 sig figs. We do the math. We write out whatever it says. Then go back and round it off. I would encourage you to always write down an unrounded version of the number. So we look at these 5 and 3. Our answer should only have 3 sig figs, so then we're going to round it. Questions? Adding and subtracting, your answer will have the same number of decimal places. So adding and subtracting, we're looking at the fewest decimal places in the numbers we're dealing with, and that's how many decimal places your answer should have. So if I look at these numbers, there's no operation sign there, but it's adding. and I'm adding those, I look at decimal places. So this has 3 decimal places. This one has 2 decimal places. It only has 1 significant figure, but I am not counting sig figs. I'm counting how many decimal places over does that number go. That has 2 decimal places. This has 4 decimal places. Do the math on your calculator, write the whole thing down. This one has 2 decimal places, so I'm going to round the answer to 2 decimal places. Okay? So that makes sense for some people. Great. If that makes sense, just plug your ears for the rest of this. I want to show you why, because some of you need to know why so that you can remember it. So if we stack them all up, we don't normally do that when we're using a calculator, stack them all up, line up the decimal points. If we think about these numbers, the last digit, the last significant figure is the uncertain digit, right? So in this measurement, 2.345, which digit is uncertain? The 5. I'm going to underline that. It's a shorthand, it's not universal, but I use it in this class. Underline the last significant figure, the uncertain digit. In 0.07, which digit is uncertain? The 7. In 2.9975, the 5. So when I think about adding, if I'm adding without the calculator, so I'm adding this column over here, what's in this next space? We have to assume 0. But is it actually 0? No. We have no clue, right? We have no clue what that really is. To be able to do the math, we assume 0, but we have no clue. And over here, we have less than no clue about that one. And then there's the 5, and we're not even sure about that. So when we add up 2 complete unknowns and a 5, and we get 5, are we certain of the 5? Absolutely not. This is an uncertain digit. Would you agree with me? Okay. So when we look at this next column, here we have a 5 that we're uncertain of. We're adding it to something we know nothing about. And then we're adding it to a 7 that we are sure of. We end up with 12. Are we certain that this is a 2? No. There's a ton of uncertainty in that. So go over to the next column. Are we certain about the 4? Yeah. Are we certain about the 7? No, that's an estimated digit. Are we certain about the 9? Yeah. So we add those together. This 1 also has uncertainty in it because of the 7. You with me? Look at this next one. 3, is there any uncertainty in this 0? No. It's not counted as a significant figure, but we know that it's 0. 3, 0, and 9, we know what they are. So when we add those up and we get a 4 in this place, we are certain about the 4. And that's going to be true of everything to the left of this. So when I look at the digits here, I want to include in my answer all the certain digits and the first uncertain. The 5 and the 4 are certain. The 1 is the first uncertain digit. So I want to keep that one. And that's why I round it to 5.41. If you didn't understand that, that's fine. Another less thinking way, you stack them all up, you look at which number ends first. This is like the, I don't know. My thinker isn't working right now. Like the most simple method. Just find out which number ends first. Draw a vertical line to the right of that through everything. You have to line stuff up to do this. You do your math, you keep everything in the correct columns, and wherever that line is in your answer, that's where you stop. So that might work for you. So let's look at this one. 5.9 minus 0.221. Do it on the calculator. It's great to be able to do math without the calculator. And if you want to stay in practice, do it in your head, but check yourself in the calculator. So you write this down. Okay, we have different methods of thinking about this. The first one is count the number of decimal places. Well, this one has 1 decimal place. This one has 3. And so our answer should have the fewest decimal places, so it has 1. We're going to write this as 5.7 because we're keeping this 6. And when we look at the next digit, that's 5 or greater, which tells us that 5.679 is closer to 5.7 than it is to 5.6. You learned about rounding in elementary school. That was a long time ago. You may have forgotten. So if you find that you're making rounding errors, please come and talk to me. I will not make fun of you. I promise. We all need help. I forget stuff too. Or you can do the line method, and that's going to tell us we need to end after the first decimal place. Okay, so adding and subtracting, we're looking at decimal places. Multiplying and dividing, we're counting sig figs. So what about the rounding? Simple, we're just going with the very basic rules. So you look at the number you're going to keep, and you may have to round it up or leave it alone. It's just called rounding down. So you look at the first digit that you're going to drop. You could think of that as the deciding digit. If that digit is 4 or less, you leave the other digit alone. You round down. If the first digit that's getting dropped is 5 or greater, you round up. It's really important that you not change the magnitude of the number when you round. This happens so much. Be very careful when rounding to the tens place or higher. What do I mean by that? Well, let's say I have this number, and the 4 is actually the last sig fig, the uncertain digit. What is the name of the place that the 4 is in? Remember place names? This is the hundreds place. So quick review of place names. Here's the decimal point. To the left, we go 1, 10, 100, 1,000, million, etc. To the right, tenths, hundredths, thousandths. Okay? So here I'm rounding something in the hundreds place. That is in the tens place or higher. Be careful. So this is what I would recommend that you do. So here's what I'm rounding. This is the decider. I look at the decider and say, well, that's less than 5. I'm going to round down. So this digit stays the same. And then all the places between this digit and the decimal point, I have to replace with zeros. So I'm going to put a 0 here and a 0 here. Once I get to the decimal point, I'm not going to write the decimal point, and I'm not going to write anything after it. That will maintain the same size of the number. Because it's this 15,426.5. So I could round this to 15,400. That's about the same, right? What I sometimes see happening is that students will tell me it's 154 meters. Which, if you put your thinking cap on, is ridiculous, right? 154 is nowhere close to 15,000. But our thinking cap doesn't always connect when we're doing chemistry problems. So just watch out for this. Any questions? Examples. So we're instructed to round each of these numbers to 2 sig figs. So we're going to keep 2 sig figs. So what you might do is underline the one you're keeping. So that would be the second one in each of these numbers. To round, you're going to look, oh, I missed the top one. To round, you're going to look at the next digit. So I'm going to keep the 3. The decider is the next one. The decider is a 7. I round up. So I make the 3 into a 4. It's 5.4. 5.34. I'm keeping this place. The 4 is smaller than 5. It's 4 less, so I round down. So this is 5.3. 5.35. I'm keeping the 3. I'm looking at the next place to decide. That's 5 or greater. I round up. 5.349. Keeping the 3. I look at the next decimal place. I look at the 4. Don't look at anything after that. Only look at that first digit. The rest of those are complete garbage. Sometimes students want to start at the end and round their way up and down, and that can actually get you the wrong answer. Because if you did that, you'd take the 9 and round the 4 up to a 5, and then that would make you round the 3 up to a 4. Don't do that. Take the simple approach, just the first one. So the first digit's a 4, so we're going to round down to 5.3. Questions?